Marini, usually known as Donatello. Donatello is a very well-established numerical mathematician. He's been producing important work for nearly 50 years. He got her degree in Korea, where she is now, back in 1970. She published her first paper in 1972, sul calcolo numerico della soluzione del problema di diversità con dati singolari.
Right.
There's too many papers in Italian since that time. She's been at the University of Pavia almost the whole time, spending time in what used to be called IAN, Institute of Analisi Numerica, which was really a beacon for numerical analysis for many, many years, and still goes on under the new name of IMATI. And after time also in the University of Pavia, which is where she holds her appointment now, although I guess she's officially an emeritus professor there. After that paper in 1972, well, I'll pick up some highlights. In 1985, there was a singly authored paper on an implementation of what was called a Rabier-Coma method. Sounds sort of like a boring title, but it's actually related to methods in ways that surprised a lot of people and brought a lot of illumination. That's an important paper still. In 1985, was also a good year because that's when the papers of the so-called GDM method came out. That's the Marini method, which is one of the important mixed finite element methods. As you know, my finite element periodic table, there are two columns of elements based on simplest roots, and one of those columns for us is the PR lambda K method, but that's the GDM method. It's one of the fundamental mixed methods that exists. And then in 2001, she wrote a paper which was the most cited paper in all of mathematics, because the math was used by a wide margin, like 30%. That was a paper on discontinuous corrective methods of unified analysis, and it was written with 4 co-authors, and 3 of them, including Donatello in this room, so definitely the other ones. And besides which methods and PG methods, she did very important works on plates, so some methods on right and minimum plates and other technical cell models. And then in recent years, her testing has been focused on virtual element methods. There's written some important papers in that way, really, because he is the center of that activity. There's one of the papers with the beautiful name of the hexahedra's guide to the virtual element methods. That's a popular one. And today we're going to hear about this new scientific computing technology, virtual element methods.
Thank you very much, Doug, for your nice introduction. And thank you all for coming. I'm delighted to be here and honored of receiving this Kirk Fellowship. So today I want to present the virtual element method, which is a recent technology introduced by my group of research for dealing with the numerical solution of partial differential equations. But before that, entering the details of the method, I'd like to give you an idea of what the role of numerical analysis is in scientific computing. So this is the plan. After a brief motivation, after a brief introduction, I will recall a couple of classical methods, numerical methods for PDEs, namely finite difference and the finite element methods. In particular, finite elements are sort of introductory to the virtual element method, and I will show this new method on a simple model problem. I will make comparison with finite elements, and then forget the 5th point. I don't think I will have time to speak about that, but tomorrow there will be a specific talk on serendipity, serendipity virtual element. And of course, I will present, by Franco Brezzi, I will present numerical results. So what are the problems? Here I listed a few examples of problems we have to deal with. On the left, you see a military plane. I was looking for a sticker. A military plane that they want to improve continuously. They want to make them faster and faster, silent, invisible to radar, unmanned, and so on. here on the right, a beautiful airplane, the Boeing 777, which is very interesting because it was the first airplane entirely designed on the computer without any test on the wind tunnel. Here in the naval and automobile industry, here you see a boat, a beautiful boat, the Oracle, running in the America's Cup. This is the latest Ferrari model, very nice, which is doing finally pretty well. And those are very complicated. Maybe they have numerical simulation, they decided to have some. These problems are very complicated because of the shapes, you see. You have to discretize all these parts. And then another example, two examples, very different in scale. Here you see an application in medicine, a taxus stent. This is a drug-eluting coronary stent, very, very small. The length is about 16 millimeter, and up there, the longest bridge in the world, connected Hong Kong to Macau. It's about 55 kilometers long, and it contains 3 islands, 1 tunnel, and there the numerical simulation has been very, very huge. Okay, given the problem, we have to translate it into equations that describe sufficiently well the problem and the problem that we have to deal with, taking into account all the physical properties. Usually, these problems are described by partial differential equation. Here you see an example, Navier-Stokes equations, which govern all the fluid dynamics problems for incompressible fluid. You see that there are 4 equations, nonlinear, time-dependent. The unknown are the 3 components of the velocity, u, v, and w, and the pressure P. And the last equation is the incompressibility condition. They're very complicated, and this is the way engineers like to write them. We mathematicians prefer this more compact and surely more elegant form, which in a sense sort of hides the difficulty, but they are there, of course. Capital U contains is the vector containing the 3 components of the velocity. And the last one is, the second equation, is the divergence-free condition. Another example, Maxwell equations, very well known, that rule all the electromagnetics problem. So these are just a couple of examples. There are many more, but I think that's enough. Now, paraphrasing Fourier, an equation as beautiful as it can be is useless unless you can solve it. And there is no doubt that these equations cannot be solved with paper and pencil. And so this is where numerical analysis enter the game, trying to find proper, suitable, discrete numerical schemes to approximate the solution in a reliable way. Now, forget this equation. I'm not going to show you numerical schemes for these equations. I'm going to use a very, very simple example. Suppose that we want to see how the temperature distributes in a room. You have a room, this, what's the color? Blue, light blue stuff. Here we have a heater at 50 degrees. There you have a window at 0 degree, and all the other walls are well isolated, so there is no dispersion of heat. We know that at regime, so after some time, when the situation has become stable, the temperature is the solution of Laplace T equals 0. Laplace is the second order differential operator, sum of the second derivative with respect to x and with respect to y, plus the boundary condition. Now, we want to see how the temperature distributes, so what do? We split the room into cells, for example, 5 by 5, and look for the solution at the intersecting points. A reasonable choice would be at each intersecting point, we decide that the value is the average of the 4 neighbors. Reasonable. And we do that, we obtain a system of 36 linear equations that the computer solves in a microsecond and produces a list of 36 values, which are meaningless unless we interpret them properly. So we have to visualize them properly, otherwise they are meaningless. So we try this representation, putting a little circle around each point with the corresponding value of the temperature and different color, from the blue one, 0 degree, up to the red one, 50 degrees. But this does not represent very well the distribution, so we try another way. This putting a square instead of a circle, and this, in our opinion, shows better how the temperature is distributed. So we keep going. We make a subdivision into 50 by 50 cells, and this is a good and very nice representation of the equilibrium solution. So this that I used is the finite difference method, which is the oldest method introduced, and mathematically it consists in approximating the second derivative with respect to x and with respect to y with the second order incremental quotient using Taylor expansion. So oldest and good, but not always. There is always a but. There is no method working for all seasons. If your computational domain is geometrically complex, is not the union of rectangles, or if we have a problem not like easy like this one, but with variable coefficients, other methods might be preferable. So there came the finite element method, which was introduced by engineers in the 60s, and then widely and deeply analyzed by mathematicians in different kinds of finite elements. Here I'm just sticking on the classical finite elements. So again, a model problem similar to what we had before. Omega is our computational domain. We have a source given f square integrable, and we look for the solution of Laplace u equal f, and for simplicity, 0 boundary conditions. To describe the finite element, first of all, we have to transform this problem into a different formulation called variational or weak formulation. We can proceed like this. We take the differential equation multiplied by a function v regular enough and integrate over omega. Then we integrate by parts the left integral. We obtain grad u grad v plus a boundary term. Now, the boundary conditions that we have do not tell us anything about the normal derivative of the solution u. So to get rid of that annoying integral, we can choose the test function v vanishing on the boundary, exactly like the exact solution does. Then our variational formulation is this one. This is the typical way of writing a variational formulation. A bilinear form on the left and a linear functional on the right, where the bilinear form is the integral grad u grad v, and fv is the integral fv. And H10 is the space of square integrable functions with first derivative also square integrable, and 0 on the boundary. thanks to a lemma called Lax-Milgram lemma, we have existence and uniqueness of this formulation, and under more regularity assumption on the solution, the variational problem is equivalent to the original one. So this is the starting point for introducing finite elements. Here again our problem. First thing to do is to produce a decomposition of omega typically into triangles, but also quads. Here you see an example. There are some assumptions on the triangulation. Two elements can have in common either one edge or one vertex or nothing. And too long and thin triangles are forbidden. But anyway, we have a decomposition. I really should have a pointer. This is too long. Anyway, H. What is H? H tells you how fine is the mesh. You can think of H as the longest edge in the decomposition, for instance. Then to this triangulation, we associate a finite dimensional space that is supposed to be an thank you. Thank you, Paul. It's supposed to be, we replace the continuous functional space here with a finite dimensional space that we want to be a subspace and is made of continuous piecewise polynomial of degree 1, 2, 3, etc. On each element we have, this is the choice with finite elements. The solution will be approximated with continuous piecewise polynomial function. How do we individuate an element, a function in this space here? Well, it depends on the degree. Suppose, for instance, degree 1, these are two neighboring elements. It is enough to assign the values at the vertices of the decomposition. Indeed, on each triangle, given the value at the three vertices, you individuate a unique plane. And then the difference of the two linear polynomial on the restriction of the difference onto the common edge is a polynomial of degree 1 vanishing at the two endpoints. So the continuity is preserved. For k equal 2, you will need to have also, for example, values at the midpoint of the edges. And if you go higher with the degree, you will need also some internal values. Those are called degrees of freedom. Degrees of freedom are values that allows you to, are sufficient to individuate uniquely a function of this space. And then what do? Well, we have to define a discrete bilinear form defined on this discrete space, an approximation of the right-hand side in such a way that the discrete problem, which is written here, variational discrete problem, has unique solution and optimal estimates holds. There are, well, the assumption on the mesh, I already said something. There are two fundamental properties to be satisfied: consistency and stability. Stability is easy. Essentially, it tells you that the discrete bilinear form has to scale like the continuous one. In our case, in our model problem, this will be automatically satisfied because AH, we don't have any variable coefficients, so we take the exact AH will coincide with the exact continuous bilinear form. And then consistency. In general, we say that a scheme is consistent, a numerical scheme is consistent if when you apply it to the exact solution, you make an error which is small, a consistency error which measures the distance between continuous and discrete variational formulation. This error has to be small, actually more precisely, has to go to 0 as h, the mesh size, goes to 0. In our case, the consistency error is 0 because there will be this strong consistency, which is actually called Galerkin orthogonality. Now, if these two hypotheses are satisfied, the discrete problem has a unique solution and optimal error estimates hold. This is a kind of interpolation error. This is the error in the right-hand side, and this is the consistency error, if any. And the consequence of this bound is that the discrete solution converges to the exact solution in this norm like a power of h, precisely like h to the power k, if k is the degree of polynomials that you have decided to use. Good. So as I said, finite elements are a very powerful method, and I think that they are still the most widely used in the codes, both commercial and free. But here too there is a but. There are classes of applications where the use of polygonal decomposition, not just simplicial grids, could help a lot. Let me give you some examples. This is a list of classes of problems where polygonal, or in general, polytopal elements can be of help. Let me give you some practical examples. Here you see an oil reservoir. Typically, when you want to recover oil, they inject a fluid, typically water, which is supposed to push the oil, to guide the oil through the recovery well. If you push too strongly, you risk to recover just water. If you are too slow, you get nothing. So here the numerical simulation is very important. And you see this is a huge domain which is made of rocks of different materials, different size, and if you want to go with finite elements, you have to and use a tetrahedral decomposition. Each of these rocks must be cut into tetrahedra, and the thing is going to be very, very expensive. Or if you have a reentrant corner, you know that the solution has a singularity here, so you need to use a very fine mesh around here. And with classical finite elements, this fine mesh spreads, has to continue here if you want to be finite element continuous. Or if you want to adapt your mesh to vortices, this is even worse. Or, this is an academic example, you want to follow a moving object at each time step. If you are not obliged to use just triangles or quads, you can adapt very easily the mesh to the object. You see, this is not a square. It's a polygon with 1, 2, 3, 4, 5 edges. This you can do if you are polygonal. You cannot if you are finite element. Or if you need to have a finer mesh around in some part of the domain, you can easily combine a fine grid with a coarse one. Here you see plenty of squares, but they are not all squares. These 1, 2, 3, and 4 apparently squares are heptagons, polygons with 7 edges. And this you can do if you are polygonal. Or if you want to follow a fracture or a crack propagation, or if you have a boundary layer, you can, those are very complicated problems, you can just use a very fine mesh here. I will show you also some numerical results. And the transition elements here are polygon with 7 edges. So there are a number of problems, applications where the possibility of using polygonals instead of simplicial grids is preferable. Here's a list of a number of various approaches to polygonal and polyhedral meshes. In the last line I collected the methods which are in the spirit of finite element type. But all of them, except them, they either are completely discontinuous or non-conforming, meaning with some weak continuity. Completely discontinuous, for example, DG, discontinuous Galerkin, or hybridizable discontinuous Galerkin, they are completely discontinuous. HHO, hybrid high-order methods are non-conforming. As far as I know, them are the only one that allows you to use polygonal grids and be continuous. Of course, you can have discontinuous them, non-conforming them, but the main feature, to my, at least in my opinion, is that you can still be continuous. This doesn't work. Okay, now, just in few words, a comparison between virtual elements and finite elements. There are a lot of similarity. The starting point is the same. It's a Galerkin method, meaning that we start from the variational formulation of a given problem. Polynomials of degree k are included in both cases, and the accuracy is the same, dictated by the degree of the polynomials inside your discrete space. The differences, well, with them, the local spaces are not reduced to polynomials. They contain other functions which are not polynomial, and to know them, we should solve some local PDE problems, but we don't want to do that. It would be too expensive, and I will show you that we don't need to compute this non-polynomial function, not even in an approximate way. Well, the grid of polygons can be of almost arbitrary shape, and what is also interesting, it's easy to construct high regularity approximation, meaning C1, C2. I'm not aware of C2 finite elements. There are a few C1 finite elements, but they are very difficult to construct. This is the first paper published on the virtual element that you can download from my web page. And here it's a long list of, not exhaustive, of useful publication for different applications that are there. I'm not going to discuss them, but they are there for the online version. So people interested can look at it. So finally, let us see what are these virtual elements. Continuous problem, let me recall you that is the same model problem. Grade U, grade V equal FV. First, we decompose omega into polygons that I call E. Then, as before, as for finite elements, we need to define a finite dimensional space, subspace of the continuous one, and such that on each element it contains polynomials of degree k, 1, 2, 3, etc. And then we go like with finite elements. Once we have defined this space, we have to define the discrete bilinear form and approximation of the right-hand side in such a way that the discrete problem has a unique solution and optimal error estimates hold. Now, let us see some examples of the composition that we can deal with. In red here are the differences with finite elements. Polygons as opposed to triangles, and the local spaces contains polynomials of degree k instead of being reduced to polynomial of degree k. This is an example. It's a Voronoi decomposition, very easy to obtain. This is another Voronoi decomposition, just finer. this is a decomposition into distorted quads, coarser and finer. This is very bad. You can treat it with finite elements, but you have to handle it with care. Now, if you think that this decomposition is ugly to deal with, what about this one? A 2x2 Pegasus. If you have in your group a guy with a lot of imagination, he takes inspiration for an Escher painting and decide to produce a mesh made of horses, Pegasus. 2x2 or 4x4, 20x20, even crazier, 40x40. And then we test our virtual element on that crazy grid. Again, on the model problem, we took as exact solution this one, which is plotted here, and then use our low-order virtual element. And believe it or not, it works. It works well. This is the approximate solution, and this is the error in L infinity, the maximum error, about 8%. Not bad for a linear method and a mesh like that. And if you go 40x40, the error decreases about 3%. So we are very happy. Now, this clearly is just to amaze your friends. Nobody would be so insane to use a decomposition like that, but, you know, it's nice to see that we can deal with it. Now, let us be serious and make some assumptions. The assumptions on the mesh, as you can imagine, are very, very mild. Essentially, every element, they can be also non-convex, has to be star-shaped with respect to a ball not too small. Okay. And these assumptions actually are needed to derive interpolation estimates, theoretically. As for the discrete bilinear form that we need to construct, we have the same two properties, consistency and stability, that we had in finite elements. Stability is the same. The discrete bilinear form has to scale like the continuous one, and consistency here is a bit different. We ask consistency onto polynomials. Polynomials are inside our spaces, and we want that on each element, if one of the entry is a polynomial, we want our discrete form, bilinear form, to be exact, to reproduce polynomials. These are the two assumptions on the bilinear form, and under this assumption we have a theorem that states that the discrete problem has a unique solution and optimal error estimates hold. This is again some interpolation estimate. This is the error in the approximation of the right-hand side, and this is measuring somewhat the distance from polynomials of degree k, element by element. Here you have a proof that I'm going to skip, of course, but it's there for people. It's easy because you see it's a series of equality, so easy to follow. Now let us construct the spaces and the bilinear form. On each element, our space is made of functions which are continuous, polynomials of degree k on each edge, and to fix the dimension, to have a finite dimension, for example, Laplace also polynomial of some degree. The degree here, k, is bigger than or equal to 1, and this k delta can take the values from k minus 2 up to k. The degrees of freedom are this one. Well, d1 and d2 are exactly what we had with finite elements, just written in a different way. And this is an additional degree of freedom in case you have this value k delta greater than or equal to 0. Clearly, you see that with this definition, polynomials of degree k are included, because a polynomial of degree k has trace of degree k, and the Laplace is a polynomial of degree k minus 2. the global space, again for this model problem. Now I choose this k delta, take the easiest case, equal to k minus 2. So the global space is made of continuous functions, 0 on the boundary, which are polynomial of degree k on each edge of the decomposition with Laplace of degree k minus 2. And again, it's easy to see that element by element, polynomials of degree k are included. What are the degrees of freedom? Well, it depends on the degree k. For k equal 1, simply the values at the vertices. So we will have 5 functions here, the 3 polynomials of degree 1, 1xy, plus 2 functions, which we don't know and we don't want to compute. These functions have a piecewise linear continuous trace and they are harmonic inside. Having defined the space, we have now to construct a discrete bilinear form which is supposed to approximate the continuous one, which is this one, and can be written as the sum of integrals grad on each element of the decomposition. And we make an observation very interesting. If one of the 2 entries in this bilinear form is a polynomial of degree 1, then by integration by parts, you go on the boundary. This integral is computable because this is constant on each edge and v is linear on each edge. So if one of the 2 entries is a polynomial of degree 1, which is inside this space, element by element, we can take as discrete bilinear form the exact one. We could. We will not do that, but another example, k equal 2, same definition of the global space. In this case, we have values at the vertices, values at the midpoint of the edges, plus a degree of freedom inside, typically the average. Again, polynomial of degree 2 are clearly inside. And as before, we have to construct the discrete bilinear form. Again, if one of the 2 is a polynomial of degree 2, by integration by parts, we obtain on the boundary something that is computable because they are line integral edge by edge. And inside, Laplace of AP2 is constant, and we have that among the degrees of freedom. So again, if one of the 2 is a polynomial of degree 2, we know how to compute, how to construct the discrete bilinear form. What we don't know to do is to construct the bilinear form, the discrete bilinear form, when both are virtual functions. For example, here we have 11 functions. The polynomial of degree 2 are inside, they are 6, but then there are 5 additional functions that we don't want to compute exactly. So what do we do? Well, there is a recipe with virtual element. When you don't know what to do, either you integrate by parts and go on the boundary, or you project. Let us project. So let me define an operator that I call, that's fundamental, operator that we call pi nabla k from h1 of each element onto the polynomial of degree k, defined as the solution of this equation here. Grad equal integral of grad v q for all q polynomial of degree k. Please notice that, well, the left-hand side is computable, is integral of polynomials. And the right-hand side is also computable by the degrees of freedom of v, because integration by parts, we obtain v Laplace q. Laplace q is a polynomial of degree k minus 1. We have that among the degrees of freedom, and this on the boundary is computable. So we know how to solve this problem. This is a sort of elliptic projection and defines this polynomial pi nabla k up to a constant. So this is a way to fix the constant. There are other ways. Then, thanks to Pythagoras theorem, we notice that the continuous bilinear form can be split as the sum of two pieces. A piece is here which is computable because those two are polynomials, and the piece which is not computable because we don't want to know UH or VH in general inside. So we are going to approximate this part. This will be exact, and it will represent the consistency part of the method, and this we are going to approximate. And I'm going to do it with something that I call S, like stability. It is any, in principle, symmetric bilinear form that scales like the continuous bilinear form. If you make this choice for your discrete bilinear form, you have consistency and stability. So, to summarize, this is the virtual space, defined, collecting, gluing together all the local spaces. This is how our discrete bilinear form is defined, and I didn't tell you how to choose S. For example, you can choose this S as the integral on the boundary. There, you know, or properly scaled. There, you know to compute integrals of polynomials. Or what we call Doffy-Doffy, you can take just the sum over all the degrees of freedom of the product of the degrees of freedom of the two functions. So you don't need to know the function, just their degrees of freedom. And then approximation of the right-hand side, there you have plenty of possibility. You can take, for instance, any projection of the functions VH, for example, this pinabla already constructed. Now let me show you some numerical results. This is an advection-dominated case. Epsilon is the diffusion coefficient, very small with respect to the transport vector, which is this vector here. Now this is on a square, 0, 1, 0, 1. On the left, on the edge x equals 0, we have this boundary value, which is supposed to be transported along this direction to the opposite edge, x equal 1, where p has to be 0, so we expect a boundary layer. And with them, let me show you. You can do, as I showed at the beginning, a mesh like that. Very, very fine, triangular mesh. All triangles here and triangles here, but very fine. And the transition elements here are polygons with I don't know how many edges, a lot of edges. You can do that, and this is the solution that you obtain. Perfect. No wiggles, no overshooting, no undershooting. While with finite elements, if you don't do like something like SUPG or suitable stabilization, you cannot do that. Same with polygons and triangles. Again, beautiful solution. Square and triangles, beautiful solution. Now, to show you that we can treat also three-dimensional problem, I'm going to show you just one example. Take a diffusion, reaction, advection operator with variable coefficients, k, b, beta, and gamma, which is written here. As exact solution, we took this one, and of course the data are chosen accordingly. These are examples of meshes that were used from the very structured to a random one. Here you see the interior, and you see that the interior of the random one is really ugly. Then we plot the convergence curve for different degree 1, 2, 3, and 4, and plotted the error in H1 and L2 for, this is for the structured field. It goes well. Similar for the intermediate one, good slope. The slope that we expect, and also for the random. But what is nice, not only the slopes are the right one as we expect, the numbers are the same. The values of the error is the same. So the method is really robust to distortion. Now, comparison with finite element. On triangles, we wanted to see what happens if you have, by chance, a triangular grid, which is a particular polygon. Now, for degree 1, we have the same degrees of freedom. Degree 2, we lose. We have an internal degree of freedom, while here, no. If you go higher, the situation gets worse. For k equal 3, we have 3 internal DOF, and here only 1. On quads, the situation is the other way around. We go a little better than finite elements, probably because we are pk, and here it's qk. So I'm going to skip the serendipity part, but I just want to tell you in few words what it is. Serendipity is a procedure very much used in finite elements to eliminate the internal degrees of freedom. This is very important, especially when you go 3D, because you want to eliminate the degrees of freedom onto the faces. We did that and succeeded, of course, otherwise I wouldn't be here and telling you what we did. So let me skip it. And this is what you obtain, exactly the same number of degrees of freedom in finite elements. And also, on quads, we have the same degrees of freedom of the serendipity finite elements analyzed by Doug Arnold and Gerard Avanou. So you see, same number. But here we win with respect to those, because it is known that finite elements suffer from distortion. There is a loss of accuracy, while we do not. And I will conclude with this for k equal 3. What we have here? Well, in green, the complete finite elements of degree k separately in each variable. We expect for k equal 3 in L2 or order of precision 4, so this is a good slope 4. This, in blue, the serendipity quads. And you see that we lose something. While with in red we have the serendipity VAM, and they superimpose with the original finite elements. And the same is true for k equal 4, and so on. But you see that the reduction in number of degrees of freedom is enormous. You go from 16 to 8. And of course, the same number, finite elements and virtual elements. So conclusion, virtual element is a new toy to play with, and I enjoy doing that. Here I've listed some of the properties. Let me underline, for example, this fact. This is very important. They are extremely robust to element distortion. There is a great generality of element shapes, as you have seen, and it's easy, although I didn't talk about that, it's easy to construct high continuity scheme like C1 and C2. And last but not least, even on simple geometries like triangles and quads, they can often provide better properties than finite elements. Thank you for your attention.
Well, it takes a lot of courage to end the lecture where you name the chairman's elements, and then you show that your elements eat them badly. Nonetheless, I'd like to thank
I didn't know you were the chairman.
We used an example that was made by you. Yes, that's correct. Absolutely. Are there any questions?
Do you recognize this?
one of your own colleagues got caught in the
Yeah.
trap as well. Are there any questions for Donatello?
It's very robust with distortion.
Yeah.
That's a numerical evidence of the algorithm theory.
I mean, this is one.
I'm talking about the way it's distorted, maybe it's not.
Oh, long and thin?
Yeah.
No problem.
Is any analysis?
No. No. The only assumption that we need is star shapedness.
But it's not shaped regular, maybe it's maybe very long, thin stuff. But it looks very robust. But
Yeah. But
when you do the proof,
let me see if
quality of stuff.
I wanted to show at the beginning the distorted quads, because there are some elements really very bad. No, it was before. Here. I don't know if you can see them.
They look very distorted.
They look very distorted. Look at this one, for instance, is long. This one is long.
Triangular elements are very distorted. When you use the standard finite element, then you use your virtual element. Would you do a comparison?
We didn't try that.
I mean,
But we have-
very well for, if you have, for instance, a small edge.
Yeah.
Small edges.
Yeah, they have to be not too many.
You mentioned, this long and straight and thin. This, in a sense, goes against the star shape. The star shape is that to a ball which is not too small.
Not too small, yeah.
So then it's
So
then you kind of not that.
you squeeze the ball.
You can be longer and thinner than finite elements, but not too much.
But the internal ball, the diameter is that proportional to the diameter of the element. That's
Yeah.
the shape regularity.
Yeah.
So if you're too thin, you squeeze the ball.
Okay.
Please.
So, Donatello, in your example, you had the additional degrees of freedom of change because they solve the Laplace equation. on the
Yeah,
side.
you have.
Does it have to be liquid in the middle, or can you have other things that are adapted
No.
to the problem at hand?
No, you can, the condition Laplace polynomial of a certain degree is there just to fix the dimension. You could use any other equation that you want. You can use, I don't know, uxx plus 2y uyy instead of the Laplace.
So that's elliptic.
Yes, elliptic.
Your original equation, just to
We did that for when we did this linear elasticity problem. Inside we used exactly the equation that we had, but it's up to you. It's not necessary to choose a precise equation, provided it's elliptic.
it has to be liquid.
Yes.
Other questions? Okay, if not before thanking Donatello again, I just want to mention that building on this lecture, there's a whole little workshop tomorrow, 5 or 6 lectures, starting at 9, I believe.
Yeah.
So we'll see you at 5. Get here at 9. Get here at 9 So I hope to see many of you there, and thanks again to Donatello for a nice lecture.
Thank you. Thank you.